Today I'm going to be talking to you about some new encryption standards that are bringing us more encryption, more privacy, and unfortunately, more malware. So our agenda for today, we're going to cover some new encryption protocols that have recently been standardized and are starting to appear on our networks. Then we're going to talk about how they change network visibility so that people who are defending networked information systems understand what they have to look for. Then my colleague Blake is going to talk about indicators of compromise that show up in these protocols, how they're different than the previous indicators of compromise that are used for malware hunting and threat detection. And finally, he's going to talk about a new technology, TLS fingerprinting, that can compensate for the loss of visibility that we've seen from these other trends. And then we're going to wrap up with some conclusions. So the new encryption protocols that are really interesting are TLS version 1.3 and DNS over HTTPS, which is called DOH for short, DOH, and then also QUIC, which is a recent IETF standard that is based on the previous Google QUIC protocol. So TLS 1.3 is used for secure web communication, and it's also used for machine-to-machine communication, secure transport. It has lower latency than previous versions of TLS, and it's more secure because it uses only modern cryptography and forward security. So it brings these benefits, and it also brings some privacy against ISPs, internet service providers, and other network snoopers, because it encrypts the server certificate. I'll be talking more about that in a few slides. The next protocol, DOH, is used for secure domain name lookups. So DNS, you can ask DNS for an IP address by giving it a host name, and it'll return that value to you. That's its typical use case. And DOH does that securely so that a network snooper can't tell what host name you're looking up. It provides privacy against ISPs and other network snoopers. And lastly, QUIC is a secure web protocol like TLS, but one with more performance advantages even than TLS 1.3 has. So it has lower latency, but it also does multiplexing of multiple data streams across a single secure connection without blocking, which means that it's a performance advantage. And it also allows connection migration, meaning that you can make a quick connection on a Wi-Fi interface and then migrate it to a 5G interface, right? Which is a nice advantage. So all of these protocols are on the internet today, and they're all increasing in their usage, right? And deserve to be increasing because of these benefits that they bring. So what does it look like when we actually use these protocols on the wire? Let's start with secure web using DNS. So this is probably the most common secure web on your network today. So here we have a user with a device on an enterprise network on the left-hand side there, and our user wants to make a connection to www.example.com. And so the first thing that happens is the user's device sends out a DNS query for asking for the IP address for www.example.com. So that DNS query is on the wire. You can see we've illustrated visibility in blue on the right. And the enterprise runs a DNS server that it uses to enforce visibility and control, right? So the enterprise can detect malware by using DNS IOCs. And so since example.com is not malicious, the query is passed to the ISP, the address is returned. The address of the www.example.com is really the address of a content distribution network. And so the TLS connection is made to the CDN server, and the TLS server name appears in that request. You can see that's visible as well, highlighted in blue on the right. And so the CDN then directs the query to example.com, and then the session is made. So this is the most typical way that secure web is done now. What happens when we bring in DNS over HTTPS? Well, now the DNS encrypted connection goes to the CDN. Typically, this is the way Cloudflare and Mozilla initially introduced this protocol. And the enterprise DNS system, which was previously being used for visibility and control, is no longer able to see that request. However, the TLS server name does still carry that name, and it carries it in the clear. It's not encrypted. So this is the high-level picture. Why don't we look at the broad changes to visibility? So it's a little bit of an eye chart, but this table shows the visibility of the server name for an encrypted web connection for all these different combinations of protocols that you can see on the left there. So in the DNS query column, we're showing clear and encrypted to indicate whether or not that combination of protocols encrypts the DNS query that would contain the server name. And similarly, the server name column in the middle indicates that in most cases, in all of the cases that are widely deployed, we have the TLS server name is in the clear. And on the right, we have the TLS server certificate, which is the digital certificate that authenticates the server. And in TLS 1.3 or in Quick, it's going to be encrypted. However, in many cases, you can obtain the certificate of a server merely by querying it and in a distinct session from the session. So if you wanted to get visibility into the certificate, in many cases, it is possible to get that. So the last row here illustrates there's something called ECH, or Encrypted Client Hello, which is an IETF proposal that's been made by some CDNs that would encrypt the TLS server name. So it might be encrypted in the future. Today, it's not really encrypted, and there are a lot of hurdles, a lot of technical hurdles to actually achieving that encryption. So this is the picture now, and the TLS server name is really important because it's not encrypted, and it carries the indicators of compromise that we're used to using with DNS. So let me talk about the bigger picture for just a minute here. These new protocols are bringing us communication privacy benefits, and these are good benefits. There are also some pitfalls, and the pitfalls are that the people defending networked information systems that contain my private data and your private data are having a harder time defending these systems because malware can more easily evade detection using the same communication hiding techniques that these new encrypted protocols provide us. So if you're interested in reading more, I encourage you to read this reference, Adopting Encrypted DNS in Enterprise Environments, which recommends doing encrypted DNS in a way that an enterprise can retain policy control. With that, let me turn it over to my colleague Blake to talk about more of the real details.
Thank you, David. So now I'm going to talk about identifying malware with indicators of compromise, given some of these new encryption standards that are coming along. So first, I'm going to talk about the SolarWinds incident, which is relatively recent, and to give you some idea of how this attack looks from the point of view of network data, let's go over that right now. So the infected host initially sends a DNS query with the name avsvmcloud.com. The subdomain of that request encodes some information about the endpoint. When the attacker sees that DNS request, it will determine whether it finds that endpoint interesting or not. And if it is interesting, it will point that endpoint to its second stage. So it will respond with a DNS CNAME record pointing to the second stage infrastructure, in this case, seobundlekit.com. The infected client will then initiate a TLS handshake where we can see the indicator of compromise seobundlekit.com in both the TLS client hello and the server name extension, and in the server certificate and the subject and the subject alternative name extension. So a couple of interesting things here. From a passive DNS point of view, if you're only looking at DNS requests, you can see the infected host reaching out to the command and control server, but you can't tell whether or not the command and control server decided whether that endpoint was worth attacking. The next point is that if the attacker were to use DNS over HTTPS, all DNS visibility would be gone. So we wouldn't be able to see the query or the response. But not all is lost because we can still look at the TLS server name. So we have those indicators of compromise from the client hello and the certificate, which in TLS 1.3, we can see it. So the next evasive technique that I'm going to talk about is domain fronting. And so this works by the malicious endpoint initially sending a DNS request for some benign domain. So in this case, example.com. Once it gets the IP address, it will initiate a TLS handshake to the CDN that hosts example.com. So we can see in the server name and the server certificate, the example.com name. So, and this is where it gets really interesting. So the malicious endpoint will send an encrypted HTTP request to the CDN where the inner HTTP host field is set to the malicious domain. And so in cases where the CDN both supports domain fronting and hosts the benign and malicious domain, the attacker is able to set up a covert channel to malware.com where we wouldn't be able to see any of those indicators in the clear. And so there are a couple of ways to still get some visibility into domain fronting, and I'm going to talk about one of them later, TLS fingerprinting. But now let's look at some auxiliary information that could be useful. And so this slide is showing the relative prevalence between malware and benign connections going to different autonomous systems. And this is interesting in the sense that some autonomous systems host CDNs that either support or don't support domain fronting. So we can use this information to build second-level detectors where we see connections going to autonomous systems or CDNs that support domain fronting. We've been tracking malware's shift to using TLS versus unencrypted HTTP for quite a while. This slide is specifically looking at malware's use of TLS 1.3 capable libraries. And over the past year, we've seen a more consistent use of malware families. We've seen more consistent TLS 1.3 use by malware families. And this peaked a couple of weeks ago. Around 40% of the malware samples that we saw were using a TLS 1.3 capable client to communicate. So the next evasive technique that I'm going to talk about is domain faking. And in this example, what we observed were a number of different endpoints infected by malware communicating to a single IP address. In each one of these cases, the endpoint communicated to the IP address using a different server name. So from a big data point of view, this was relatively easy to detect because what we did was associate all server names to IP addresses. And the thing that kind of jumps out at you is that we have an IP address hosting very different domains that we wouldn't expect to be hosted by a single IP address, in the sense that we wouldn't expect this IP address to host Amazon.com and Google.com. So this is pretty suspicious. And going one step further, if we wanted to develop techniques that could identify this type of behavior on a single session basis, we could look a little deeper into what's actually happening on the client and the endpoint. And specifically, what we saw was a TLS fingerprint that contained offered cipher suites that were not legitimate. So the cipher suite codes in the TLS client hello did not map to any known cipher suites. And then when the server responded, not only was the selected cipher suite of the server, not only did it not map to any known cipher suite codes, but it also wasn't in the offered list. And finally, the server responded with a certificate that did match the server name. So if the client requested Amazon.com, the server would respond with an Amazon.com certificate, but it was expired. So taking all of these facts into consideration, doing a single session domain faking identification is relatively easy. So now I'm going to talk about our implementation of TLS fingerprinting. So we have something we call TLS fingerprinting with destination context. And similar to other approaches, We derive a fingerprint string from the initial TLS client hello packet. So we look at the offered version, cipher suites, and TLS extensions to generate our fingerprint string. Unlike other approaches, we also incorporate the destination context. So this allows us to disambiguate amongst all of the processes that are using the same fingerprint. And with our system, we facilitate high efficacy client process identification, operating system identification, and the ability to detect malware. And to give a little more intuition around why destination context matters, this is a real example from real data. And so this is the S-channel TLS fingerprint string. It's one of the more popular TLS fingerprint strings. S-channel is the default library for Windows. And in this example, there were hundreds of processes that map to this same fingerprint string. But by using the destination context, we're able to disambiguate the set of processes and differentiate things like Microsoft Office using this fingerprint string versus malware. And secondly, by using the fingerprint string, we can actually divvy up all of the processes that map to that fingerprint string, and we're able to detect malware even when it goes to suspicious or benign sites in some cases. For example, we're able to detect malware going to google.com or dropbox.com when it uses a suspicious TLS fingerprint string. Okay, and now back to you, David, to wrap it up.
Thank you, Blake. I'll take us out with some conclusions. So I want to mention that the TLS fingerprinting with destination context is available today, provided by Cisco in the form of an open source package that's called Mercury, and it's available on GitHub. And we're currently integrating this technology into Firepower 7.1, planning a beta for the fall of 2021. So if you're interested in learning more about fingerprinting and what it can do for you, I hope that you reach out to somebody from Cisco about that. So the high level conclusions are that we are going to see more encryption from these new standards, and there's a lot of positives in that. There's more communication privacy against ISPs and governments and other network snoopers. But there's a downside as well, which is that malware can use these new encryption standards to hide its communication as well. So we need to be aware that we can look for indicators of compromise in the TLS server name and in TLS server certificates as well. Domain fronting can hide some of these indicators of compromise, so we need to be aware of that. And lastly, TLS fingerprinting is especially interesting because it can regain some of the visibility lost to these new standards. So I want to remind you, you can continue your education at Cisco Live by demos in the Cisco campus and participating in one-on-one Meet the Engineer meetings. There's also walk-in labs and other related sessions that you can participate in. So I hope you have a great Cisco Live, and I want to thank you for your attention today.